Section 11.7, fluids in motion. So now we're getting to the point where everything will start moving, no longer static. So the motion we're going to consider here is going to be steady flow, where the velocity of the fluid particles at any point is constant as time passes. So if we look at point 1, the particles that are passing through point 1 will have a velocity of positive 2 meters per second. At point 2, at that location, the velocity of the particles will always have 0.5 meters per second. We don't need to worry about it being something like unsteady flow, where the velocity of fluid particles at a point changes as time passes. Like at one instant, it's 2 meters per second. Another instant, you look at that same point and all of a sudden the particles are moving faster. It's like, wait, how'd that happen? What's going on here? The most extreme of this would be turbulent flow. It's an extreme version of unsteady flow where the velocity of the fluid particles at a point changes erratically in both magnitude and direction. This is chaotic motion, right? Where you don't know where the particles are going to go at any given point. We're going to be focusing on steady flow here. Now, fluid flow can be compressible or incompressible, right? Compressible meaning you're changing the density, right? Most liquids are nearly incompressible, and we're going to be focusing on incompressible fluid flow. Compressible, as the fluid is moving, makes things more complicated. Fluid flow also could be viscous or non-viscous. The viscous is referring to the stickiness of it, right? So like honey is a very viscous substance, super sticky. How much does it stick to the sides? So we're going to be using an idealized fluid that is always incompressible and non-viscous, does not stick to the sides, smooth moving. You could add those considerations in further down the road. It just makes them more complicated, right? Steady flow is a great assumption to make because plenty of cases are nearly steady flow. If you want to study turbulence, you could get a PhD studying turbulence because it's that complex and complicated. Now, when you do have this steady flow, you'll often use streamlines to represent the trajectories of the fluid particles. So rather than drawing a whole bunch of points and where the particle is going at that point, you can just draw a line and say, hey, the particle travels along this line. So that's some helpful notation as we're going through this. Let's take a look at fluids in motion with our next section. 11.8, the equation of continuity. The equation of continuity is getting at something you've observed if you've ever used a garden hose without a little attachment at the end, right? If you just turn on the garden hose and you have water coming out, what happens if you stick your thumb over the end of it? When you stick your thumb over the end of it, the water suddenly starts going further, right? You can get it across the yard to the far corner versus before it was just kind of dribbling out the front. What's going on here with this garden hose? Is it magic? Well, you might consider it magic, but it's also physics. So the mass of the fluid per second that flows through a tube is called the mass flow rate. And that's going to help us with explaining this garden hose. So mass flow rate is going to be mass per second, so kilograms per second. That's worth keeping in mind. So let's look at that. The change in mass over the change in time is going to be our mass flow rate. Change in mass we can calculate with the density times the volume. How much volume is getting through? Well, that's going to depend on how fast the fluid is moving, right? The cross-sectional area is constant, A, that's shown here. And then the distance, so the length of that cylinder, can be calculated with the speed that the fluid is moving times the time interval delta t. So if we look at the mass flow rate at point 2, right, the change in mass over time, where we've just divided this time over to the left, we find that it's equal to the density at point 2 times the cross-sectional area at 2 times the velocity at point 2. We can do the same thing for a fluid at another section of this tube, right? Notice now the tube has narrowed, and so it has a different cross-sectional area, A1, a different velocity, V1. And so it's a different length of tube, V1 times delta T. So if we divide the delta T across, we get that the mass flow rate at section 1 is the density times the area times the velocity. Now the equation of continuity says that the mass flow rate has the same value at every position along a tube that has a single entry and single exit. So as long as you just have a single tube, then the mass flow rate needs to be the same throughout that tube. So that means we can set the mass flow rate at point 1 equal to the mass flow rate at point 2. This is our equation. Now, what is the SI unit of mass flow rate? Well, it's going to be the change in mass over the change in time. So sure enough, it's going to be kilograms per second. And you can show that these quantities will give you kilograms per over seconds. So this is a handy equation, but even handier than this perhaps is some of the sub-equations that can come from it. If we have an incompressible fluid, which for our purposes, the fluids are all going to be incompressible, we can use this equation instead, which does not have density, because we don't have to worry about the density changing at different points in the motion. This is a really great equation. What does this say? Well, this says that depending on the cross-sectional area of the tube, the speed will change of the fluid as it goes through. So for instance, but it needs to stay constant, that ratio. So if your cross-sectional area increases, if it gets much bigger, then to keep this ratio of area times velocity constant, the speed is going to have to decrease. Similarly, if the area decreases, we see that the speed will then increase to keep the two in balance. And that's what's shown in this figure, right? Notice when it's really wide, the large cross-sectional area, it's a pretty small velocity. V2 is not very big. At point 1, it's a much smaller, narrower tube, so it's a smaller area, and V1 is much larger because it needs to get all that mass through in the same amount of time. This cross-sectional area times velocity is known as the volume flow rate, which could be noted with a Q, but I don't see much reason to use a Q. I think it's better instead to write it as a change in volume. The main thing you have to be careful of is that this is a capital V, not the lowercase v like the velocity, divided by a change in time. So the volume flow rate is constant for an incompressible fluid. All right, now that we have this information, let's take a look at that garden hose again. Example 12, a garden hose. A garden hose has an unobstructed opening with a cross-sectional area of 2.85 times 10 to the negative 4 square meters. It fills a bucket with a volume of 8.0 times 10 to the minus 3 cubic meters in 30 seconds. Find the speed of the water that leaves the hose through A, the unobstructed opening, and B, an obstructed opening with half as much area. So notice, it's asking us to find speed, so we want to find V. What's the difference between the two cases? Case A, it's an unobstructed opening, so it's just nice and wide. Case B, obstructed opening with half as much area. So the area has gotten smaller in case B. So what do we expect to happen if the area gets smaller? I want you to think about that. What else do we have? We have the unobstructed area, so we have the default area, and then we have this volume of the bucket and it says it gets filled in 30 seconds. So how can we use that? Notice that's volume and time. We can use a change in volume over a change in time. That'll be our volume flow rate. Right? We know that the change in volume divided by the change in time should be equal to the cross-sectional area times the speed. So that will allow us to then solve for the speed V. So this is looking pretty good. Let's give it a shot. Right, so V is equal to the volume flow rate divided by the cross-sectional area, and the volume flow rate is calculated with the change in volume divided by the time, and the area is in there, and so then that comes out to a speed of 0.936 meters per second. In case B, our area is now going to be half as big as case A. So we could go through the same process and just plug in an area that's half as big. That's entirely valid. We can also use our incompressible flow version of the equation of continuity and compare the two. So we can solve for V2, the velocity in part B compared with the velocity in part A. And all we have to do is put in the right ratio of areas, right? Noting that the area in case 2 is 1/2 that of the area in the previous case. So if we divide A1 divided by A2, we would find that it is A1 divided by 1/2 A1. So the A1s there would actually just cancel out, and we'd be left with 1 divided by 1/2. It can be really tempting to say that this is just 1/2, so you have to be careful there. If in doubt, you can plug into your calculator 1 divided by 0.5. Because indeed, if we wanted to get rid of this fraction in the denominator, we want to multiply by the reciprocal of it. So 1 times 2/1. And that indeed shows us that it's just 2. And so that's what they plugged in here. 2 times the speed that we got in part A, 0.936 meters per second. So the speed is now twice as big as we got in the previous case, in case A. It's 1.87 meters per second. And this is what happens with the garden hose, right? When you stick your thumb over the end of it, you're reducing that cross-sectional area, but the mass flow rate needs to stay the same. It needs to stay constant. So the speed of the fluid increases to keep the mass flow rate constant. That's why this equation, the continuity equation, is so powerful, because it says that the only thing that affects the speed of a fluid is the cross-sectional area available to it. So if you want to figure out how fast a fluid is going, you want to think of this equation first and say, hey, do I know the areas? Can I then figure out how fast my fluid is moving? And we'll see how this will work in conjunction with the equation we get in the next section.